Hi everyone. Let's talk about the first derivative test, a test we use to determine if a critical number gives us a local maximum, local minimum, or neither. In the first exercise, we must find all critical numbers of the following function, and then we must determine if those critical numbers correspond to local maxima, local minima, or neither. If you would like to try this exercise on your own, stop the video now. You can also download these notes using the link in the video description. I believe that this function has many critical numbers. I see a critical number -4, -2, -1, 0, and 1. -4, -2, and 0 are critical numbers because that is where the derivative of the function is 0. The numbers -1 and 1 are critical numbers because these are the places where the derivative of the function does not exist. We have a corner. Some of these critical numbers correspond to local maxima, some of them to local minima, some of them to neither. -4 corresponds to a minimum. -2 corresponds to a maximum. -1 corresponds to a minimum. 0 corresponds to neither, and that is because no matter how small of an interval around 0 you consider, the points on the left side of the critical number, or the values of the function on the left side of the critical number, are always below the value of the function at 0, and the values of the function on the right side of the critical number are always above the value of the function at x equal to 0. So, the critical number x equal to 0 gives us neither. Finally, at x equal to 1, we also get neither. The values on the left side are smaller, the values on the right side are bigger. How can we easily identify if a critical number gives us a local maximum, local minimum, or neither? One way to do it is to think about what happens to the derivative before the critical number and after the critical number. For example, right before -4, the function is decreasing here. All the slopes of tangent lines are negative, meaning the derivative there is negative. And right after that critical number, the derivative is positive. The function is increasing, which means that at this critical number, where we have a local minimum, the derivative changes sign from being negative to being positive. Take a look what happens at the maximum. Again, on the left side, I have the derivative that is positive. On the right side of that critical number, I have the derivative that is negative. I go from a positive derivative to negative derivative, which means if the derivative changes sign from plus to minus at that critical number, then we have a local maximum. What happens if the derivative doesn't change sign? For example, right here. Take a look. Right before that critical number, the derivative was greater than 0. Right after that critical number, the derivative is still greater than 0 because both here and here the function is increasing. This suggests that if the derivative doesn't change the sign at the critical number, then the critical number gives us neither. This is exactly the statement of the first derivative test. Given a critical number of a continuous function f, if the derivative changes sign from positive to negative, then f has a local maximum. Think about that. If the derivative changes sign from positive to negative, that means that the function went from increasing to decreasing. That's why we must have a local maximum. If the derivative changes sign from negative to positive, meaning the original function goes from decreasing to increasing, then f gives us a local minimum at c. Finally, if the derivative is positive on both sides near c or negative on both sides of near c, the sign of the derivative doesn't change, then f has no local maximum or minimum at c. Let's see if we can apply the first derivative test to a problem. In this exercise, we must find all local maxima and minima of the following function and we must justify our answer by using the first derivative test. If you would like to try this problem on your own, stop the video now. We know that local maxima and minima of functions occur at the critical numbers. Let's first find the critical numbers. To do so, I find the derivative first, and I get 4x to the third power minus 12x squared. Then I ask myself two questions. Are there any x's for which this derivative does not exist? And are there any x's for which this derivative equals 0? Because this derivative is a polynomial, it exists everywhere. You can plug in any x, meaning the first condition gives us no critical numbers. There are no x's that make this derivative undefined. To find x's for which this derivative equals 0, I will set the derivative equal to 0, and I get 4x to the third power minus 12x squared equals 0. To solve it, let me factor 4x squared from both terms, and I get 4x squared, and in parentheses, what I have left with is x from the first term, negative 3 from the second term. This tells me that this function has two critical numbers, x equal to 0 and x equal to 3. To visualize this, I will draw the x-axis and I will add my critical numbers to it. The critical numbers are 0 and 3. These critical numbers split the x-axis into 3 intervals. To determine if 0 gives me a local max, local min, or neither, I need to see what happens to the derivative around 0. According to the first derivative test, if the derivative on the left side of 0 is positive and the derivative on the right side of 0 is negative, this suggests that the function goes from increasing to decreasing, telling you that you have a local max at 0. If the derivative goes from negative to positive, the function goes from decreasing to increasing, giving you a local min. And if the derivative goes from positive to positive or from negative to negative, then 0 gives you neither max nor min. To determine the sign of the derivative around 0 and around 3, I create a table. In the first column of the table, I will add the intervals created by the critical numbers, and the intervals are negative infinity to 0, 0 to 3, and 3 to infinity. Now, I need to come up with a test point from each interval. Any number that is in the first interval, any number that is in the second interval, and any number that is in the third interval. I believe that the first interval has a number inside of it, for example, negative 1. I also know that 1 is in the second interval and 4 is in the third interval. In the last column, I will determine the sign of the derivative. When I plug in negative 1 to the derivative, which is the same thing as plugging it in here, I get negative 1. When I plug it here, I get a positive number. When I plug in negative 1 here, I get a negative number. Positive number times a negative number gives me a negative number. When I use 1 and I plug it in to the derivative, I will get positive number times a negative number. That gives me a negative number. When I plug in 4, I will get positive number times a positive number, which gives me a positive number. In the first interval, the derivative is negative. In the second interval, the derivative is negative. In the last interval, the derivative is positive. By the first derivative test, we know that 0 gives us neither max or min, because the derivative doesn't change sign. It goes from negative to negative. On the other hand, 3 must give us either max or min. Let's ask ourselves, is this number giving us max or min? The derivative goes from negative to positive, meaning the function goes from decreasing to increasing. You must get a local min. 3 gives us a local min, and that is because the derivative goes from being negative to being positive. The goal was to find the local minimum. So let me now plug in 3 to the function and I see what exactly that value is. F of 3 is. Let's see what we will get if we plug in 3. I take 3 and I plug it into the original equation and I get 81 minus 4 times 27 is 108. 81 minus 108 is negative 27. Negative 27 plus 1 gives me negative 26, which means that negative 26 is your local minimum.